discussing. The topics I'll be covering, I'll first start off talking about heat transfer, and then we saw the spray modeling yesterday. Today I'll talk about some of the spray combustion research, and that leads then into diesel combustion modeling. And then finally, I'll talk about optimization and low temperature combustion. Okay, so engine heat transfer. I've already mentioned, okay. Better? Thanks. I've already mentioned heat transfer in the context of super knock in gasoline engines. Heat transfer is a big deal. About 30% of the fuel energy can be lost to wall heat transfer, and that number is approximate. There are ways of reducing that, and there are ways, obviously, of increasing that. The issue we saw yesterday is that heat transfer can also influence temperatures in the chamber, and therefore both ignition and knock. And it can obviously impact the durability of an engine and can lead to catastrophic engine failure, kind of like you see in these pictures. You see here that in this particular case, parts of the piston were actually melting and burning away. In fact, some years ago, we had an engine in our lab where the student turned off the fueling, and the engine kept running, and eventually we found it was running on aluminum. Basically, the piston had melted and was supplying the fuel. So it can be disastrous. And the other thing is little things can happen, like this little crack you see here due to thermal gradients, which can seriously impact the performance of an engine and its durability. So I want to just talk a little bit about heat transfer, and we want to talk also about radiation. Here's our energy equation for the internal energy. We've already seen the pressure, volume, work term, the heat diffusion terms, the dissipation of energy term, the energy release or source term due to combustion, source term due to spray, and now just briefly I want to talk about radiation as well. In particular, radiation is important because in the participating medium in the combustion chamber, radiation can either be absorbed or emitted and reach the walls, and that obviously impacts heat transfer as well. So you might have a wall here, you might have a cell close to the wall, and you of course have convective and diffusive heat transfer. From the Reynolds analogy, there's also a connection between heat transfer and momentum transfer or wall stresses. And those appear in models for heat transfer. So for example, we've shown that for compressible flows, the appropriate form for the wall heat transfer involves logarithms of temperature, the gas temperature above the wall and the wall temperature, and this non-dimensional coordinate y plus, which is basically related to the size of the cell, the friction velocity, which comes from the square root of the turbulent kinetic energy at the boundary, and viscosity. So when you have radiation, you have to kind of rethink this and realize that there are other source terms, like I showed you yesterday, that involve the combustion source term at the wall. You might have combustion going on, and radiation. So in the case of radiation, we want to include the radiative heat flux in the calculation of the wall heat flux. Once, of course, we have the wall heat flux, we can calculate the gradient of temperature at the wall, which is obviously of interest. The radiative source term involves the radiation intensity at the position R in the direction omega. Omega is a solid angle, and the black body radiation, and then an absorption coefficient. So how do you get that? Well, we solve the radiation transfer equation, which is shown here. It looks, I guess, a little similar to the energy equation, except that here we're talking about the radiation energy at the point R in the direction capital omega. Remember, radiation travels at the speed of light, so you're not going to be looking at the same type of equation that you'd have for fluid mechanics. The terms on the right-hand side involve radiation transfer due to absorption and outscattering. So here's your absorption term. This is a scattering term. Then there's the black body emission from each point in the domain. And then a term involving inscattering. So basically radiation arriving at a point is then scattered in various directions due to its participation with the media, the gases at the point of interest. And here's your Stefan Boltzmann constant. So this is the equation that you have to solve. And typically in engine research, it's been shown that the scattering terms are relatively small, and we focus mostly on the absorption and black body emission terms. The method that's used to solve the equation varies, depends on whose paper you read, but we've found that the discrete ordinates method is very useful. So what one does is, let's say you're interested in this point here, you collect radiation that comes from these 6 directions or surfaces, and then radiation passes out through those same surfaces. And you do this for every computational cell in the domain. You basically resolve in the direction cosines, the first term here, the gradient of the intensity, with certain weights associated with the number of ordinates that you've chosen. In the example here, there's 6. So what about the absorption and radiation of soot, from soot and from the gases? The total absorption coefficient is the sum of the absorption due to soot and then absorption due to participating gas phase species, CO2, water, and others. For example, you might want to include CO as well. And this is the Beer-Lambert law, which says that the absorption in the gas is a function of temperature, pressure, and the path length of the radiation, and the emissivity term, which basically is going to be contributed to by emissivity due to the fuel and all of the participating gases. So we need to look at each of those individually. So looking at soot absorption, the typical expression that you'll see is that it's a constant times temperature. So it's relatively simple. But for the gases, and that's because it's essentially a continuum radiation, but for the gases, we have to worry about the fact that they have typically absorption bands, like here you see for CO2 at certain wavelengths. You'll see absorption and emission of radiation. And the approach that we've often used is the so-called wide band models, where you represent these absorption bands with some kind of an expression with constants chosen to match the spectroscopic data. And once you have that, you can then plug that in over here and calculate the absorption coefficient due to that particular species. If you look at the equation, it turns out that its dependence is more or less inverse with temperature for the gas phase, but proportional to temperature for the soot. So if you go back to the radiative source term in the equation, you'll see, just looking at the predominant absorption terms and ignoring the scattering terms, that it's made up, as I say, of the gas and the soot contributions times the T to the 4th for the radiation. And taking into account these dependencies, you see that the gas contributes proportional to T cubed, and the soot contributes proportional to T to the 5th. So that means that soot, if you have a lot of it, can be a significant contributor to radiative emission. And that's also depends on path lengths and various other parameters, pressure, temperature. So it turns out that in our experience for standard diesel combustion, this is often the predominant source. Whereas for low temperature combustion, where there's not much soot, the gas radiation contribution dominates. So putting all of that together, one can form a sort of a mean absorption coefficient that accounts for the gases, CO2, water, CO, and so on, as a function of temperature, and use this then in our final evaluation of the absorption coefficient. That includes the gas and the soot. The soot radiation as a function of wavelength comes from the Rayleigh theory and involves the soot number frequency volume fraction and wavelength of the light, the radiation, and then the index of refraction, the complex index of refraction. So with all of that available, we can then solve the radiative transfer equation with all of this input data. The other thing that's important, now that we know the contribution due to convection, conduction, and radiation at the surfaces of our combustion chamber, is what is the actual temperature of the piston wall, the liner, and head, and so on. And that we calculate using a code that allows us to perform conjugate heat transfer analysis. So here you see the mesh, say just for the piston. The boundary condition is from the gas phase. You might have some kind of combustion process. And this then contributes heat flux to the surfaces, both through radiation, convection, conduction. And then we solve for the corresponding heat conduction, taking into account boundary conditions such as the oil cooling jets below the piston, and so on. So when you do the calculation, turns out that you have to do it as in an iterative step. You use your gas phase code, like we use Kiva in this example, your CFD code, to provide heat flux, which is then input into the heat conduction in components conjugate heat transfer code, which then calculates the surface temperatures, which you had to assume back here. And now you have updated surface temperatures. You now recalculate the heat flux, and so on. And it turns out that within 2 or 3 iterations, you can get the surface temperature of the combustion chamber pretty well analyzed. So here just shows an example of the calculated surface temperature on the piston after going through a couple of iterations. You see, obviously, down here it's cool. It's oil-cooled piston in the gallery regions. And then where the spray impinged and you have some pretty violent combustion, you'll see higher wall temperatures. And this shows another engine with the same concentration of heat at the lip of the piston bowl, which is, by the way, where a lot of failures occur in these engines if you don't control the heat transfer paths in the piston. Okay, so what's the big deal? How does this influence engine operation? So here we have a plot of peak piston temperature versus start of injection timing in a diesel engine. The solid symbols that you see here are without considering radiation. We've started out assuming a constant temperature piston at each point. And then after the iterations, we wind up with this result down here showing, well, actually, it's the middle one, showing the converged, we consider it converged temperature of the piston, peak temperature of the piston for each start of injection timing. If we had, I'm sorry, that's without radiation. If we had included radiation, now you have significant heat addition due to radiation, and you see significant increase in the predicted temperatures. I guess this one here is what we consider the converged temperature. It's 100 degrees higher or close to it. Maybe, sorry, 40 degrees higher. So total heat loss is increased in this case by 30% due to radiation. Depending on where you are, the head increase was 34%, the liner 19%, and the piston 47%. So that energy that now went into the wall actually lowers the bulk gas temperatures, which results in lower nitric oxide, but higher soot, because with lower temperatures, you generally form more soot. So it's kind of important to include these effects if you want to be predictive. So here we see, corresponding to this plot, the prediction of the NOx. Obviously, with early injection timing, you have lots of time for formation of NOx. You get high NOx levels. So with radiation, we get the black curves here. If we had ignored radiation, let's see if I got it the right way around. Oh, these are with two different equivalence ratios, two different loads. So let's just pick one of them. The open symbols is the higher load case. The square here would be no radiation and with radiation. Then this is the reduction in NOx that you see due to the decrease in temperature. Depending, of course, on the equivalence ratio, you'll see more or less than that. Okay, so the bottom line is that heat transfer is important in engines, and actually later I'm going to show you some results with low temperature combustion engines where we try to minimize heat transfer and heat losses to the maximum extent, and this has an impact on combustion efficiencies. So, spray combustion research. There's a huge effort pioneered at the Sandia National Lab by Lyle Pickett's group, the Engine Combustion Network, or ECN, where they have, on their website, categorized the performance of diesel sprays over wide ranges of operating conditions. And that data is available for anybody doing modeling work or other experimentalists to compare the results for diesel, other fuels, various temperatures, chamber densities, and so on. So you can see from the side view, here's the injector, here's the spray. If you view through these windows, you can see they have intake, spark, exhaust, pressure transducer, and then a mixing fan to make sure that the conditions are more or less homogeneous in the chamber at the time of injection. And this just shows an example, some calculations we did of the injected spray here. The penetration of the vapor versus time is shown here. The black is the experimental data. There's some uncertainty around that. The experimental uncertainty is shown in gray. And the red is the CFD. And then the liquid penetrates a certain distance, and that comparison with the experiment is also quite good for this particular case. So that data is used, as I say, widely. A real good understanding of diesel combustion came in 1997 with John Deck's work at Sandia, where basically he tried to explain some of the features that had been seen, namely from the heat release curve, you see this premixed burn, and then another peak, which is called the diffusion burn. And how did this come about? Well, if you look at his results, these are kind of from his experimental paper, you see the liquid in black penetrating and surrounded by some vapor. And this continues for quite a while from the start of injection. And then at a certain moment, you'll start to see the beginning of combustion. And that combustion process basically consumes all of the vapor that has been created up to that time in a bang, creating the premixed burn. And then after that stage, you've pretty much burned the pre-formed fuel or fuel vapor. And now the combustion rate is determined by how fast you keep supplying fresh fuel. So at steady state, what you would see is your liquid fuel, air being entrained into the spray, the liquid spray, a certain length of liquid called the liquid length, and a flame established around this region here, which consists of products of rich combustion. So this is not complete combustion here. This is partially burned fuel, and a thin diffusion flame that surrounds this partially burnt fuel region. And downstream, when there's been enough distance or time for soot to form, you would see soot clouds. So that was what John deduced from his laser measurements in a diesel engine. So this, he used optical diagnostics and basically concluded that if you looked at OH PLIF, for example, that it only exists around the periphery of the jet, and there's this thin diffusion flame surrounding a jet that's filled with partially burnt fuel and soot. So sometimes later, in 2006, Mark Musculus extended this to look at low temperature combustion. And although there's some similarities, there's a liquid length and there's a vapor region surrounding the liquid length, he noticed that there was a region here, kind of similar to this one, but of much more extent, that has partially burnt or partially pyrolyzed fuel, such as formaldehyde and other first-stage ignition leading compounds. And then eventually they undergo faster combustion in the second-stage combustion, and that is in this region here. One of the things that he noticed was that OH was observed in the entire region across the jet. And here you see much less soot than in this case, but soot being formed at the head of the jet. So significant differences between the conventional diesel and the low temperature combustion. So soot is, of course, of great interest to the diesel industry. And so over the years, there have been many attempts to model soot. For instance, in my group early on, we used the two-step model. I'll tell you a bit more about it in a minute, followed by a multi-step phenomenological model, and then finally a more recent PAH model. There's other models that you can read about in the literature. This is a vast field of research. So just looking at the two-step model, this was proposed by Hiro Hirasu a long time ago in '76, where basically he said that the rate of change of mass of soot due to combustion is the difference between a formation rate and an oxidation rate. The formation rate, he found experimentally, was proportional to the square root of pressure. It has an exponential dependence on temperature. And then in his case, this driving force here was the fuel mass. We found that it's better to use a species such as acetylene as the driving force. And then there's this tuning constant. So that gives you the soot formation rate. The soot oxidation rate, we've used the Nagel-Strickland-Constable oxidation rate. I'll talk more about that later, which is proportional to the soot mass, some sort of diameter of the soot density. And so calculating soot is not very arduous because it's a pretty simple model. And it's been used satisfactorily by a lot of people. However, what people have found is that there's certain aspects of the model that just don't agree that well with experiment. So for instance, when we compared the soot mass as a function of distance from the injector against the Sandia spray chamber data, what we found was that experimental soot was occurring further downstream than in the calculation. So here's some of the measurements from the Sandia constant volume vessel. As a function of temperature, first thing you notice that at low temperatures, there's no soot. And as the temperature increases, you start to see a natural luminosity indicating soot. The dashed line you see here is the lifted flame location. And you see the soot forms downstream of that. So this was the first indicator that the two-step model probably was not giving us what we wanted. So we started thinking about more complicated soot models. And in particular, if you just look at the gas phase chemistry, what you find from simulations that we did is that indeed, after the vaporization process and combustion starts, you start to see a region of formaldehyde, the precursor to the first stage combustion, followed by a soot precursor region, and the whole thing, of course, is surrounded by the flame. And that agrees pretty well with the structure seen in Sandia experiments. So that means that one has to consider in more detail soot formation. So we start from the pyrolysis process. That's this one we already saw when we were talking about hydrocarbon combustion. This leads to formation of species such as acetylene, C2H2, which then, of course, with further oxidation or compacting of the molecule produces propargyl, which then can combine to produce ring compounds. The ring compounds can eventually accumulate to form polyions, which then form the basis of the nucleation process leading to soot. The soot particles themselves can coalesce to form what are called primary particles, which can, of course, agglomerate to produce the final soot. So all of this really needs to be modeled in some way if you want to predict the final engine out soot. The process of these coalescence agglomeration, you have a competing process of oxidation where the soot is also oxidized. So what we did was to look in the literature for PAH mechanisms. That means starting from propargyl, the development of the first ring compound, benzene, and the reactions that eventually lead to A3, which is phenanthrene, and then pyrene, A4. And we extracted in Arrhenius form the appropriate constants for each of these steps. It turns out to be a 20 species, 52 reaction mechanism that helps you to predict the beginning, the PAHs that might start off toward the nucleation. So now going back to that experiment, here, this is now on a log plot, we're showing the soot mass in the experiment. Notice there's a peak here. The soot is formed, and then it's oxidized. The injector is back here. The lifted flame location is here. And here you see the soot volume fraction in parts per million. The CFD now gives fairly reasonable agreement with the measured data. And you can analyze in the CFD the species involved. So the first species to appear is the acetylene. Then comes the A1, A2, A3, A4. And in this particular case, I think these calculations used A3 as the precursor in the Hiroyasu type of, if you're thinking of a Hiroyasu type model, instead of acetylene for the soot formation. So the actual model is nothing like the two-step Hiroyasu model. Here we start with A4, the pyrene, and we create carbonaceous soot through this graphitization reaction. The rates of these reactions, again, come from the literature. And now we have acetylene-assisted surface growth, where the soot carbon, the solid carbon, through this Hacker process, hydrogen abstraction, carbon addition, produces additional soot and hydrogen. These reactions depend on things like the surface area of the soot, which you have to estimate knowing the soot particle diameter and the number of soot particles. Well, how do you get that? The soot particle diameter, you know if you know the mass and the number of particles. And so we solve, as I'll show you, a transport equation for the particle number. Then, of course, there's additional processes such as the coagulation of soot as the nucleation particles grow. It also depends on the number of particles. Then we have the oxidation processes. The oxidation due to oxygen, that's the Nagel-Strickland-Constable model. Here are all the constants associated with that. And then OH-assisted oxidation, where soot can be oxidized by the presence of OH. Again, the temperature, the mass fraction of OH, and some parameters of the model, surface area, all of those things appear in the model. And then, of course, we have the PAH-assisted surface growth, similar to the acetylene surface growth, and many more parameters. Okay, so with all of that model input, we have now source terms in a transport equation written here. This transport equation is written in terms of, there's two of them. One for the soot species density, where M is rho times YC, the soot, solid soot mass fraction. And another identical equation for the soot number density. So this is what the equation looks like. We have a convective term, the diffusion term, the thermophoretic term. We had a question the other day about thermophoresis. That's included in the transport equation. And then source terms. And these source terms depend on whether you're dealing with the soot species density equation or the number density. For the species density equation. Those rates for the reactions that I showed you earlier are all going to contribute to and the amount of soot that's in the chamber are going to contribute to the evolution of the soot mass fraction. And the number of particles is going to be determined from this equation, which includes the diameter of the particles and a nuclei size of the particle as a normalization. So that's the soot model. Details are given by Gokul Vishwanathan's thesis work, and we found it to be quite useful, as I will show you. So going to the engine combustion network sprays, again, now, since the early days, there's been a lot more cases on the ECN website. And one of my students did some analysis for actually a wide variety of cases. I think I'll just talk about a couple of them. 900 Kelvin ambient at 15% oxygen. 21% would be air, right? So you can see this is modeling a case with some exhaust gas recirculation. Density, typical of a diesel engine, and an injection pressure, 150 megapascal. The models were the ones I've been telling you about. The spray breakup is the KHRT, the discrete multi-component vaporization model, the generalized RNG K epsilon for turbulence. Combustion used the speed chem package. We have droplet collision model, the near nozzle flow gas jet model, and the soot model that I've just told you about. And the grid is shown here. So this just shows some of those input conditions that applied in the ambient. And again, the vapor penetration versus time agrees very well with the experimental data. Liquid penetration versus time, again, also looking very good. These plots show the radial distribution across the jet of mixture fraction, in this case here, at 20 millimeters, 30, 40, and 50 millimeters, 20, 30, 40, 50 millimeters downstream. And also the axial profile of mixture fraction that's along the center line. You see, we do reasonably well with the axial profile, but there are some discrepancies with the radial profiles. This is something that is influenced by the turbulence model, and I'll show you some results later that actually show improvements over these, but these are still within the experimental scatter, the dashed lines in most cases. So now you've got the appropriate fuel distribution before combustion. Now let's look at the predicted soot. So here are the experiments from Sandia for 850K up to 1200K. Again, this is natural luminosity that indicates where the soot is, and one can back out from an analysis, an estimate of the soot volume fraction from this data. And down below, you see the corresponding simulation results. So first thing you notice, if you look at the liftoff lengths, these lines here, that we calculate the origin of the combustion fairly well. At least certainly the trend is correct, and even the magnitudes. And then we also predict much lower soot volume fraction for the low temperature case and much higher soot for the high temperature case. So these are actually pretty satisfying comparisons. The plots here show liftoff length versus ambient temperature. The experiments are from in the solid here. This shows, the red shows our calculation. You see there's some discrepancy, especially at low temperatures for the distance from the nozzle to the lifted flame location. However, it really depends a lot on the mechanism that you use. Here's another mechanism from the literature that gives not as good agreement as the one that we used, which Jim Wang produced. Down here, you also see just the trends of the amount of soot versus time, showing again that at low temperatures you see very little soot. After the formation, you reach a kind of a steady balance between formation and oxidation. And at high temperatures, you'll see more of that. We can use the model to kind of explore details of the model, like, for example, the surface growth rate. How important is this reaction? How important is soot particle coagulation? So we can change these constants in these rates here to see just what happens. So if we look at our baseline here, and we play with the coagulation constant, divide by 3, and we play with the surface growth by multiplying by 1.5, we see that the surface growth has much more of an effect than coagulation. So this is kind of useful because it tells you if there are uncertainties in the results, where should you be looking to try to improve your understanding or the modeling. And you can see the corresponding changes in the distribution from the baseline with these changes. The other thing, though, that these changes do is to change the predicted diameter of the particles. And that has quite a significant effect, as you can see from the changes in color here. So if, for instance, you're doing a simulation and you find that your particle diameters are, predicted particle diameters are not necessarily to your liking, you might need to tweak some of these model constants. Okay, so what I wanted to talk about here is kind of how heat transfer and spray combustion research ties into CFD modeling development. There's a lot more work that's needed. I mean, we've just discussed here how you can go from the gas phase chemistry to the inception of nuclei, which then lead to the formation of particles. We have assisted surface growth. Also, the aromatics contribute to the growth of the soot particles, which then can coagulate, producing finally the particles, and they can agglomerate and so on. And in the meantime, all of this process here is being subjected to oxidation by O2 and OH. We have extended the model also to gasoline direct injection engines. And one of the things that we had to do there was to consider pyrolysis of the fuel, the heavy components in the fuel. There's some papers that describe that. The other kind of direction for research that is highlighted by these pictures here is that soot is not just carbon. Conventional diesel has a high fraction of elemental carbon. But if you start looking at advanced combustion regimes like partially premixed compression ignition or reactivity-controlled dual-fuel compression ignition, you find that what you collect on a filter is completely different color. And part of the reason for this, we've discovered, is that these advanced combustion regimes also have organic condensed fuel that is wrapped around the soot particles. And this is shown in these transmission electron microscope pictures here, which basically show that you have not just solid carbon, but also pyrolyzed fuel elements that are part of the particulate. And that's something that really needs more study. We've done a little bit of work in that area in some of the references that you see here. So these are the references that I wanted to cover today in this first section. And we have 20 minutes, and I was thinking it would be nice if we just went around the room and just maybe if you could take 30 seconds and talk about what you do so everyone knows who you are and what you've been doing, and maybe that will help us to see the connection between your presence in this room and what I've been talking about. If you don't want to talk, just I'll ignore you. Why don't we start with you?
Can I have a closer?
Sure.
The DBI engine, is that for convenience? Okay, so we can send the model to people.
Yeah, I'm sorry, I'm 60% efficient. What? I don't think but you get 60% yesterday. The same one. Why don't you tell us what you
Okay, so my name is Fahd Zahani. I'm a PhD student at University of Michigan, Ann Arbor. So I am actually basically, so Soot is actually my field. So I'm trying to quantify soot formation from actually GTI engines as well. So I'm kind of focusing more on the role of the deposits in the engine, and specifically on the injector. So injector fouling was actually found to be affecting engine out emissions, engine out soot. So under conditions where we have no wetting of the other surfaces, injector wetting is actually one of the main, is the dominant soot formation mechanism. So I'm trying to understand that role and how the deposit building up on the injector actually affects the PM, which we see. Like as the deposit goes up the tip, soot changes. So
Okay, thank you. I'm going to move on, but that's really good. Skip something. You want to go ahead?
Oh, yeah. Hello everyone, my name is Chu Tingzhu. I'm from Yale University. We are also people. So we are looking at the switching tendency of different fields and also the relationship between different field structure with soot structure and also soot evolution, but within the plane, not within actual engines.
Okay.
And also we also do soot sampling at TM.
Hello, my name is James Strasser. I'm coming from Warsaw, Poland. So we make the engines for city protocol and power plants. My expertise is in CFD, so I do CFD mostly within civil aviation and transport.
Very good. So the people at the back and here, next guy, stand up and speak loud. No, I'm talking about him, yeah.
Everyone, my name is David Zhang. I'm from the University of Connecticut. Now, currently, I'm working on the development in the second doing model in the large area simulation to investigate the children.
Very good.
Hello everyone, I'm Zhihao from Michigan Tech. So currently we are investigating the spray water interactions, especially in the spray combustion and also the soot formation of
Hello everyone, this is Emma, and I'm also from Michigan Tech. So we are in the same group and doing the same thing. Actually, I'm not in the postdoc in our national lab. So I'm doing the 0D and 3D simulation to look at the mechanism effect and field effect on the cold side.
You're working with, well, you were working with Professor Neighbor. He was one of our students some years ago.
Yeah.
Hello everyone, my name is Shoujin Yu from the same group. I'm working on the DME high injection pressure spray and combustion characteristic in the constant volume vessel, which is in configuration with this NDI.
Thank you.
Hello everyone, I'm a leading scholar in Princeton University. My major is internal combustion engine. My research is about methanol and ethanol alternative engines.
Very good. Are you working with Xinguang?
I'm working in China, in the
But here?
University of China. I'm a visiting scholar.
Visiting scholar.
Yeah, Princeton.
Good.
Hello everyone, my name is Soya. I'm a postdoc at Princeton working with Professor Michael Mueller. So my field is also Soot. We investigate several different aspects. First thing is fundamental Soot modeling. Basically, typically people have methodal moments and sectional method. One is pretty cheap. The other one is can give you the distribution, but pretty expensive. So we are developing a hybrid one between these two to provide good performance. The other thing we're working on is the large area simulation of soot flames. The key problems when you have a large grid which do not resolve everything, you have the average mixture fraction cannot represent the mixture fraction inside the grid itself. So in most of the cases, you either significantly under predict the soot, and we figure out substitute modeling to address that.
I come from West Virginia University. My professor is Princeton. And my research is about the different combustion characteristics of vehicle gas engine modified from a diesel engine. It's a spark ignition engine. We just replace the fuel injector with a spark plug and inject the fuel into the battery before the take off. And we are evaluating the knocking phenomena, cycle-to-cycle variation, because the laminar flame speed of melting is very slow. And we are checking if the switch generated turbulence will increase the flame propagation for Princeton combustion chamber. So we are evaluating if the diesel engines, heavy-duty engines can be used to modify to vehicle gas ignition operation.
Thank you.
Hi everyone, my name is Reitz from Iowa State University, and my professor is Dr. Sun. Okay, so
He was one of my students.
yes. Right now I'm working on the direct numerical simulation of double interaction. So we hope to generate a more accurate double interaction model that can be used in NGCFD simulations.
Hi, my name is Umesh and I'm a PhD student at Reitz. I'm working on LES modeling of supercritical mixing and combustion, where I'm focusing on the subgrid modeling for scalar covariances. I do not right now work on IC engines, but this is something of my interest for the future.
You work with Professor Cenzali, maybe?
No, I work with Dr. Vigarian and Joe.
Right, but I say if you want engines.
Oh, yeah.
Right, hello everyone. My name is Petro. I'm also a PhD student at Georgia Tech. I work on solid modeling in LES for turbulent combustion. And I've also previously worked on Soot during my first year, where I investigated different solid modeling for Soot in LES with emitted opponents and the LES modeling as well. So,
Good. Also with Bigger Yang?
no, I work with Professor Freshman.
Oh.
I'm Tricia Chen. I'm a graduate student at the University of Michigan Professor Damon's group. And I'm looking at the fuel storage for jet fuels and its ignition property for coupled HCCI testing and simulation. It's like more chemistry controlled, so I can look at the detailed chemistry and ignition process of the pure components that we select to make surrogate fuels for the jet fuel.
Thank you.
Hi, my name is Kim Kim. I'm from University of Central Florida. I'm working on this major in light-burning velocity. And actually, our group working on the code generation. So I needed to understand the internet needs, so I take this.
Hi, my name is Kwang Hee. I'm a PhD student of the University of Michigan. Now I'm working on the experimental study of auto ignition of several gasoline compression ignition fuel using a variable compression ratio HCCI.
Hi, my name is Dick Berger. I'm studying in the region physics at ECN, and I'm a new PhD student, so I'm not really sure about the topic yet, but I'm interested in diesel engine combustion and diesel engine experience.
You're in the right place.
Hello everyone, I'm Abdullah Bajwa. I work in the same lab and we are currently working on coming up with new ways to estimate traffic fraction for large bore natural gas two-stroke engine. And we work with Dr. Mark Harrison from GE, who is one of your former students.
Hi, I'm Carrie Clemmer. I'm at Princeton, and I'm looking at uncertainty propagation and turbulent combustion models.
I'm Cody Nuna. I work in Michael Moore's group at Princeton University on reduced order chemistry models for large eddy simulation, and specifically how radiation in those kind of systems interacts with information.
Hello everyone, my name is Matt Montgomery. I work with Lisa Pepperly and Charles McAnally at Yale University, and we study how chemical structure influences soot formation in laminar flow diffusion flames.
Hi, I'm Ferris. I'm from CAUS, and I work with Professor Robert Durbo. I'm working the argon engine, which is an advanced technology.
So you replace the nitrogen with argon because of the high specific heat, and everybody can now notice why that's a good idea, right?
Yes.
Hey everyone, I'm Chaitanya Wadkar. I'm a student at Michigan State University. My research deals with ignition delay measurements using rapid compression machine and also comparing the data with 0D and 3D simulations.
I'm Sarush. I'm working at Indian College London. My project is experimental, and I'm working on fuel injection and normalization at cold fuel conditions, minus 10 degrees Celsius.
For diesel?
No, actually, currently in biofuels.
My name is Nick Grannon. I work for a company called Innovative Scientific Solutions in Air Force Research Labs at Wright-Patterson Air Force Base, doing small engine research, specifically with small turbojets.
I'm Justin Reinhardt. I also work for Innovative Scientific Solutions at Wright-Pat, working in the small engine research lab there.
What is the application for reconnaissance flight zone?
Yeah, there's various projects, but yeah, it's one of them.
My name is Joe Key. I'm from Cyber Research Centers. I do research on the aircraft engine combustion.
Hello, I'm Krishna from University of Illinois, Chicago. I'm working on understanding the fuel chemical structural effect on soot formation in laminar flames.
I'm Luca Henry from the University of Michigan, and I study the experimental characterization of rate of heat transfer from molecular species in spark ignition engines and motor auto engines.
Cool. I think you had the first there.
Yeah.
Hi, my name is Angela. I work in the same lab as Luca with Volker Stick, and I am working on large heavy simulations of our optical engine, looking at the near wall flow and transfer, and I'm interested in large heavy transfer modeling as well.
Hi, I'm Ahmed Mosajolo, and I also work in the same lab with Luca and Angela at Water Physics at University of Michigan. And I do horoscopic infrared imaging in heavy differential gas engines to study different ignition and flame kernel formation characteristics resulting from different ignition systems I have, including the correlate data.
My name is Rafael. I'm from Brazil. I work on quasi-dimensional models and multi-dimensional models. And in the future, I try to compare the end gas process that happens in this model.
I'm Brian. I'm from Stony Brook University, and I work with Dr. Lawler on some new low-temperature combustion concept called TSCI, which is thermally stratified compression ignition. And we try to extend the natural thermal stratification via direct water or ethanol injection during the compression stroke to help control HCCI.
Hi, I'm Dave. I'm from the same group from Stony Brook. I'm working on reformer OCCI and reformer CCI.
Okay.
My name is Carlos Romero. I work for the Universidad Tecnológica de Pereira in Colombia. I teach internal combustion engines and also mechanical design. I love internal combustion engines, but from my background, I've studied it from the point of view of mechanical systems, trying to design parts of the engines, but lately I got an insight, I try to get an insight into the combustion phenomenon, which is very important to me. Now we are working with a small engine, trying to assess the engine performance, varying the compression ratio, the ethanol content mixture, and also the compression ratio. We are working with that. He's my son.
everyone, my name is Ishan Ahmed. I'm from Aalto University, Finland, and I'm totally experimentalist. I'm working on heavy-duty optical diesel engines and as well as the single-cylinder full metal engines. And my work is mainly focused on dual-fuel combustion concepts, and we are trying with the different fuels and trying to extend the limits of lean burn combustion.
Natural gas fuel?
Yes.
You had a first to that too, I think.
Yes.
Hi, my name is Gaurav. I'm from the same group as Brian and Deva from Stony Brook University. So I do the modeling part of what Deva does. So he deals with the experimental part of the reformed RCCI combustion. I do the 3D CFD modeling of the same work. Thank you.
I'm Sriram from the University of Maryland. My work is on vortex flame interactions. Specifically, I work on flame temperature measurements and emission quantification.
Hi, my name is Mia. I'm also from Stony Brook University with those guys. And we're investigating the what is the different PRS number and what is the EGR has effect on RCCI combustion.
Hi, my name is Renee, also from Stony Brook University, and now I'm working on the single zone and multi-zone chemical kinetic simulation on a HCCI engine using primary reference field.
Hi guys, I'm Min Tongzhou from Stony Brook. Recently I'm building a predictive HCCI model with experimental data and chemical kinetics. Yeah.
Hi, Mustafa Sadun, Wayne State University. I'm working on investigating auto ignition and advanced engine or VCI engine by using optical CI.
I'm Jonathan Martin from the University of Michigan. I work on mapping out different dual fuel combustion modes in multi-cylinder conversion engines.
Okay, so we have everybody. Well, thank you very much, everybody. And I see you kept it really fine-tuned to the time, so we have 15 minutes off for me.